So this should just turn into 2. That's the 2 up top that came out. Natural log absolute value x minus 4 plus c, we're done, right? There shouldn't be a lot of time invested in something like that. Let me change it up a little bit. You have to worry about that 3 now, right? Because you still have a constant on top, you still have linear on the bottom. You can still do a u substitution. When you do this u substitution, 3x minus 4, the derivative is going to have a 3 in it, right? Which you have to kill off. So you're going to need a 1/3 in front of this whole thing. So I'm going to first do the 2 times. Now here's the 1/3 that's going to scale that thing down. And then the rest is just natural log. Yeah, I was going to. I'm just trying to show where each piece came from, right? That 2 is going to come from here. That 1/3 is the scaling of that right there. I mean, if we wanted to, couldn't we just like make up a formula on our own here? Couldn't we say something like this? Like if you ever have, let's say, some constant on top of some linear expression in x, right? Like that? That your antiderivative will always be the constant, then you'll have to scale by the 1 over a, and then natural log of that linear expression plus some constant, right? I mean, if we really wanted to generalize, that's what it would be. But I don't want you to go and try and like memorize a bunch of formulas. Again, it's more of the concept. I just want to show of hands, honestly, how many of you are following this idea? It's kind of become a little bit of a theme now in this class where we're scaling out that number. Y'all kind of getting that? Okay. All right. So are we good? Constant over linear? I think I have another one for you to try. It's not hard or anything. Okay, there you go. Try and do that one on your own. I'll give you 6 seconds. Can y'all see it? Maybe make it bigger or no? I want to hear from somebody that I don't normally hear from. So raise your hand if you have an answer. You got one? Hold on. Anyone else? I'm just going to flip to my roster and just point blindly to somebody here. Let me see. Well, Andy's not here. Lorraine? Wait. Larney? Uh-oh, I can't say the name. Bradley. Yeah, Brad. I don't remember seeing your name like that before. What? Bradley. Yeah, that's official. Okay. Do you have an answer? I believe you do. I'm gonna skip you. Okay. Anthony. Where's Anthony? No Anthony? Logan? Okay, Logan. Are you following? Okay, we'll give it a shot. Perfect. Yes or no? Yes, perfect. So we're looking at the linear expression. We see a -5 in front. We've got to scale that out, -1/5, and then the rest is just, hey, it's going to be like a 1 over u problem, right? 1 over u du. Perfect. Good. -5x plus 4. Oh, could you have written it like backwards in here? Oh, yeah, absolutely. Yep. All right, good. All right, so if we see, what?
I was going to say, so taking the sign there was really important.
Yes, that -5 has to be accounted for. Because you look at that, you could also look at that as -5x plus 4, right? If you rewrite the bottom, just rewrite it, change the order, right? Then you see that the a is negative 5. This a in front is negative 5. So you need to scale it out. The only way to make that a 1 is negative 1/5. All right, constant over linear. Constant over linear, we're in business. Next type, constant over repeated linear. And when I say repeated, I mean that it's being multiplied times itself twice, 3 times, 4 times. It's repeated. It's not just a linear expression in the bottom. So constant on top, linear expression, it's being repeated, in this case, squared dx. All right, could we still use a basic u sub and let u be the 2x plus 1? Could we still do that? Yeah. If we did that, in this case, taking the derivative, we would get a what? If we let u be 2x plus 1. I'm saying, what if we let this be u, and we take the derivative of that, what would we get out? 2 dx, right? So we're going to need to scale by a half, aren't we? No matter what, scale by a half. So let me go ahead and just put that now. I need to scale by a half. All right, now I'm looking at that and really like, this is happening in my mind. I'm seeing that instead of 1 over u, right? Instead of 1 over u, it's 1 over u squared, du. And I'm saying, shit, that's not natural log, right? But this is actually u to the negative 2, isn't it? And then I can use the power rule from earlier, right? So we add 1 to that power, and then we do 1 over. So this becomes 1 over, if we add 1 to that power, we get negative 1 u to the negative 1, right? Now, I don't know how much of that you're going to be able to do in your head, so if you can't do it in your head, you're going to have to write it down, all right? But we do want to try to get to a point where we can kind of see this all, even if we just need a real quick sketch of the integral that's going to happen. So I'm about to put this right here. I'm going to put that there. 1 over negative 1 u to the negative 1 plus c. But what's u for us? 2x plus 1. It's nicer when it's just natural log, isn't it? You don't have to worry about that. I'll just leave the answer like that. Let me do another one. What about this? I'll just change the problem a little bit. Make it the 5th power down there. So again, I see that's linear down there. I see a constant on top. I see that it's a linear expression that's being repeated. Repeated. This 5th power means being repeated 5 times. Scale by a half. Still need that. Yeah, this is really like a 1 over u to the 5th, which is really like a u to the negative 5. Sorry, 5, right? And then that, if I did the antiderivative, I'd have 1 over negative 4 u to the negative 4. Right? That's the way I'm just adding 1 to that number. So that's going to be this. 1 over negative 4 u to the negative 4 plus c 2x plus 1. I mean, we could like mechanically do the substitution, right? If we wanted to, we could sit here and say, okay, u is 2x plus 1. du is 2 dx. Let's rewrite the integral 1 over u to the 5th, and then that's off by 2, so I would scale both sides, right? This would become du, and I pull a half out. And then I could do this, right? But this is going to take time, right? And on a test that is timed, you do not have time to do this, right? So you want to get to a point where you can do it a little bit faster and faster and faster. All right, let me see what I have next. Recap. Formula 17, we see that, we're happy. Constant over linear, we're happy. Constant over repeated linear, I don't know if we're happy, but we're not crying yet. That one's the same thing. Okay, here we go. This right here is not a trick question. I just hadn't like technically written out what that form is called. So on top we have a constant, right? And on the bottom, look at what we have. We have a quadratic, right? Constant on top. We have a quadratic on the bottom. And that quadratic is missing an x term, right? You have x squared and you have a constant, but you don't have an x there, do you? Yes?
Can you look at it like x squared plus a squared?
Yeah, exactly. So this is just formula 17, the very first one I gave you, right? The very first one we talked about today. I'm just saying, I want you to look at it from the perspective right now that on top you have a constant, and on the bottom you have a quadratic that just doesn't have an x term. If you ever see that, I think formula 17 will probably work, right? Unless maybe, what if there was a minus under there? Let's answer this question first. Okay, what if I have this? This should be 1/3 inverse tangent x over 3 plus c. That's formula 17 that we started this whole thing with, right? That's no problem? But you see it, yes? Okay, now what if I change the problem to be this? 1 over x squared minus 9 dx. The formula doesn't apply, yes? Uh-huh. Yeah, if you pull a negative out, right? If you pull a negative, then all that happens is that becomes positive, but that one goes negative, so it's still not that form. So the formula 17 does not work for this, right? But the bottom is a difference of squares, yes, and it factors. Okay, but we actually do have a formula. I just never shown it to you before. And it is formula, is it 19? I forgot what oh wait, I wrote it right here. It's right here. Here's our problem, right? X squared minus 9, do y'all see it's formula 20? So 17, 19, and 20 are all very similar. I don't know why they stuck this 18 in the middle of these, but 17, 19, and 20 are all related to one another because they all have a constant on top. This one has a sum of two squares. This one has a difference of two squares where you have the constant before the variable. This one is the variable before the constant.
So if we see a constant over a quadratic
without an x term in the middle, it's going to be one of these three. It's going to be one of those three. So we're going to use this formula right here, right? I'm going to use that one right there. And let me get that out of there. So I'm going to use that formula right there. Okay? So it'll become 1 over, you said what? 1 over just 6. Yeah, because it's 2 times a. A is the number that's being squared. So for us, 3 is being squared. Not negative 3. The negative is part of the formula. Okay, so the a for us is 3, so it becomes 1/6 natural log of absolute value. Okay, u minus a, u is x, a is 3, over u is x, a is 3, plus c. Does anyone have a question on that?
So is there any way to generalize that? It's, I guess you get like a difference or difference of squares on bottom with a constant missing x term. There's a lot of words for that.
Yeah, I mean, it is, we're looking here in both of these cases, these are quadratics, and they're missing x terms, right? You just have a squared term and a constant term. If we ever see that, has to be a constant on top though, right? If we ever see that, we're in business, right? We've got these 3 formulas, either 17, 19, or 20. No? Hey, what about this? What if I take that problem, what if I had factored a negative off the bottom and turned it into 9 minus x squared instead? Right? Right? What happens? I don't use that formula anymore, do I? I use the other one, right? And what's the difference between those 2 formulas?
Which one on top?
Yeah, look at the formulas. I'll bring them back up here. Yeah, here are the two formulas right here. Do y'all see that the only difference between these two is the flipping,
Oh, yeah.
right? Yes.
Does it work if it's not like a difference of squares? Like if it was like a 7, could you just
Oh, yeah.
root 7?
Yeah, absolutely. If it was a 7, then a would be root 7, and then you just use the formula. So why is the formula just this flipped? If you change the order of this, why is it just flip that over?
Because the natural log is like, that's a subtraction of natural log.
Yeah, so when to get from here to here, we could just pull a negative out. If I pull a negative out of this, right? If I pull a negative out of this, negative goes out here. Those basically switch and become this, right? So imagine I had a negative out here, right? What would happen if I put a negative in front of a log? Well, I could push it up as a power, and if you do a power something to a -1, it flips the fraction over. I'm just showing you, like, that's why these formulas are almost identical. You technically only need one of them, because you could always factor out a negative to get to this. But either way, you got a formula. We got to move on. All right, so constant over linear, constant over repeated linear, constant over quadratic that's missing an x term. We're happy about all of those, right? Then let's see what's next. A constant over an irreducible quadratic. So let's make sure we understand what I mean by this. The top is a constant, right? 1. Could that constant be a 5 instead? Would it still be a constant? Like 5 on top, yes? And then I can just pull it out of the integral and become a 1. So I'm always using 1 here, but this could be any number. And you just pull it out and it would be back to a 1 up there. I have a constant on top. The denominator is a quadratic, and I'm saying it's irreducible. What does irreducible mean? Can't factor it. It doesn't factor. Because remember, like when you have quadratics like this, let me give you a quadratic that does factor. Right? That is a quadratic that if we mess around with the numbers, and this is Cal 2, right? So we should all be comfortable, like it shouldn't take us 20 minutes to get to this, right? Right? Like we should all be able to factor that. This one, that's what we're going to do. I don't know who said that, I just heard. Who said that? Yeah, that's what we're going to have to do. But the reason we're going to do that is because we can't factor it, okay? If we could factor it, then we're going to have another way of doing it. That's what will come next class.
Once you complete the square, does it turn to one of those 3 formulas?
It's going to turn into one of the formulas we just used, exactly. So for this, do y'all understand that we can't factor this? Like there's nothing you're going to come up with that multiplies to be 17, adds up to be 2. It's not going to happen. So we're going to complete the square. So let's complete the square over here. I'm going to do this problem. So complete the square. I take x squared plus 2x. What's the number I'm going to add and subtract?
1.
4.
I'm hearing 4 and 1.
It's 1/2.
Oh, it is 1.
Yeah.
It's 1? You take half of that number, right? Half of that number, half of 2 is 1. And square it, and you get 1. Add 1, subtract 1. I never checked to see that the leading coefficient was a 1, did I? But it was, and so that's why I didn't factor anything out, right? I noticed there was a 1 out there. These first 3 terms are guaranteed to be a perfect square trinomial, and that just means that it breaks down to be something, plus something squared. And I told you last class where that number comes from, right? Yeah. That number is exactly the number that you get when you just take half of that number. So we took half of 2 and got 1, right? That will always be that number. And then when you square it, that's the part that you add and subtract.
That's because if the the general form is 2xy for that term, or whatever.
2xy.
2xb, whatever you call it.
Yeah, like 2ab or 2xy, yeah, for the, exactly. All right, and then these two come together, right, and that gives you plus 16? Yeah? Okay, so that's what's on the bottom. I'm going to rewrite this integral. Integral 1 over, okay, I've got x plus 1, x plus 1 squared plus 16 dx. That looks a lot like formula 17, the very first one we started class with today. Well, not the first in this section, right? And what we have here is linear in here, right? That's linear. And it has a 1. Yes. That means I don't have to scale by anything, right? So I can go straight to the formula 17. Formula 17 says 1 over a, 1 over 4, because a is 4. Inverse tangent of whatever the variable is, but for us the variable is the linear expression, right? X plus 1 over 4.
Okay, so you don't carry that squared one,
What squared?
the one that's attached.
No, because the formula, right? The formula says this is like our variable squared, right? This is like u squared. So u is, this for us is the u, and that's what goes here, u over 4. What do y'all think?
This is actually
Okay? So far okay?
The only thing I was gonna ask on this one, because, so it's not gonna be like that previous one where it was 1 over 2x plus 1 squared, besides having to do the scaling.
Yeah.
But, it just had the, when you just turn to that, it's the negative 1 plus c, it's not, you're just gonna go with the number 17.
Are you saying why am I not using 19 or 20?
Yeah, I guess.
Because this isn't a minus sign. On 19 and 20, they both require minus somewhere.
I didn't even have a thing after it, so I guess I'll say it differently. Never mind.
Sure? Anyone else have a question? Sure? Over there? My quiet side of the class over here?
First fraction is always going to be like a number over a number. It shouldn't be an x.
Where, here?
Yeah.
For this particular form, you will never have an x out here, no. It'll always be a number. And for this form, it'll always be 1 over a, unless you had, like if this had been, let's say, a 3x down here, then I would have had to scale by 1/3 first, and then the rest of it would have been the same. All right, I'm going to make sure everyone's good up to this point, because it's going to get a little bit bumpy right now.
And can those be interchanged? Like
Yes. If this were written the other way around, this would be the same formula because addition is commutative, so you just, and it's the same. Nothing changes over here. Everything's the same. Subtraction, then we look at formula 19 or 20. All right, we're good? All right, this is my favorite problem of this part of this section. We have not had this yet, right? Everything up to this point has been constant over something, right? Constant over linear, constant over a linear that's repeated, a constant over a quadratic that was missing an x term, right? Constant over linear, constant over repeated linear, constant over quadratic that was missing the x term, constant over a quadratic that was irreducible. That's the 4 different things we've seen. We've not seen this yet. Here, the numerator is no longer a constant. The numerator is a linear expression in x, right? And the denominator is a quadratic that is irreducible. So I've got a linear on top, and this can't be factored. Was there a question?
Would you split them up?
Into 2 different?
Yeah.
So let me say this to you. This is a very special type of problem, linear over irreducible quadratic. I tell you, it's one of my favorites, all right? Because there's so many different ways to do this problem. There are a lot of different ways. Splitting it, okay? And you could do a completing of the square right now. There's all these different paths that you could go that I could teach. And I just happen to do it a certain way that I like. So I'm not going to say, don't split it. But the way I present it to you, please know that if you go get help in tutoring, there is a very high probability that they're not going to be familiar with what I'm going to show you. Like, they probably have not seen it. Unless they took me for this class, then they would know what you're talking about, all right? And there's a reason why I do it this way instead of the other way, And it's because it requires a certain level of like you having to think a little bit outside the box, which I think is a good thing. Yes?
Without going too into it, what do you mean what?
I think what was like x over that, and then minus 1 over that. Because if you did that, then you, well, imagine you did that. X over this, forget that one. But the 1 over this, that's like the problem we just did before, right? A constant over irreducible quadratic, you would complete the square and you would do your business, right? But it's the x over that that would be a problem, all right? Okay, so here's what I'm going to do. The method that I like. I realize the denominator is a quadratic, right? The denominator is quadratic. And I know that when I take the derivative of a quadratic, I should get a linear, right? And that's just the way derivatives work. If I have a quadratic function and I take the derivative, I'll get a linear function. So it would be awesome. Wouldn't it be awesome if I took that as my u and I took its derivative and it actually gave me that? Wouldn't that be really like nice? It'd be convenient, wouldn't it? So look, I'm going to just write it down. If I let u be the denominator right now, I'm going to cross my fingers. I'm going to cross my fingers. I'm going to hope for the best. Take the derivative of this. What's the derivative of this? 8x minus 4. I'm going to put in parentheses dx. Right? That is the derivative of the denominator, right? Shoot, we're off, right? You see that? We don't have that, do we?
You can factor the 4 and scale.
If we factor the 4 out, right? If we factor out a 4, we'll have 2x minus 1, won't we? And that's not a 2x minus 1. It's an x minus 1, right? We're close, though. We're close. We're just off a little bit. Yes? Yeah? Okay, so here's where the magic happens, all right? What I'm going to do is even though I don't have that there, I'm going to make that appear here. I'm going to make it happen, all right? So watch me like magically make this appear up here, all right? So here's what I'm going to do first. I'm taking that original integral, x minus 1 over, it's not magic, it's just algebra, but it's creative algebra. So this is what I want, right? I'm going to start by getting the 8x. And the only way to get an 8x here is to put an 8 in front of this, right? The only way to do that is to multiply the top and bottom of this thing by 8, right? So I'm going to do that, but I'm going to do it outside the integral because I want my constants on the outside. I'm going to multiply this integral by 1, which is 8 over 8. So I haven't changed the problem, have I? But I'm going to now force that 8 through the numerator. Right? I'm going to force it through. I'm going to multiply it through. I'm going to leave the 8 that's down here on the bottom. So my next line will be 1/8 integral. Now when I force that 8 through, I get 8x on top minus 8. It has to distribute to both, right? And then 4x squared minus 4x plus 3 dx. What's wrong?
I respect it.
You see what I'm doing? I'm not there yet, but do you see I'm closer?
What's the numerator?
Well, it's 8 over 8, right? 8 over 8. You could rewrite 8 over 8 as 1 over 8 times 8 over 1, right? And then I'm just taking the 8 over 1 and passing the 8 over 1 through and leaving the 8 that's on the bottom behind.
Okay.
Right? If I factor an 8 back out, it would cancel back out and you just have a 1. We're a little closer to where we want, right? I want it to be 8x minus 4. I have right now 8x minus 8, yeah? I want minus 4. There's a couple of ways I could get minus 4 right now, but again, I'm going to show you the way that I do this. I have 8x, right? I want minus 4. That's what I want. So I'm going to make it happen. Minus 4 plus 4. Then I still had there the minus 8. My goal was to try and get the numerator to have 8x minus 4 in it, right? I had gotten an 8x there, I didn't have a minus 4. So what I did was I did 8x and I made the minus 4 appear, minus 4, but I have to add 4, right? Because I can't just like subtract 4 out of nowhere. So I subtracted and added. This right here, this is in math what we call a hidden zero. It's such an important part of mathematics to see hidden zeros in places. At this level, it's not that important, but like if anyone, math majors, I don't know if I have math majors, any math majors, anyone computer science that are gonna go like further up, hidden zeros are like so important. Yes, there's a question.
It's probably a stupid question. It doesn't matter the order, right? It's hidden zero of -4.
Well, I wanted minus 4, right? That's why I put minus 4 plus 4. If this would have said plus 4, I would have done plus 4 minus 4.
Oh.
Do you see that this right here is exactly what I was hoping to see there?
Yeah.
Okay. I've made it appear, haven't I? But there's a catch. I still have some shit over here to deal with, don't I? Okay, well, that's okay. I'm going to deal with it. It won't be a problem. All right, rewriting it. Okay, here's where we are. I'm going to continue. So our integral looks like this. 1/8 integral. I've got 8x minus 4. Then when I put these two together, I get minus 4 again, right?
Yeah.
Now, I realize some of you were like, I saw that like way earlier, that the minus 8 could be written as minus 4 minus 4. Maybe you saw that. It doesn't matter. Let's just keep going. If you didn't see it, I don't want to try to confuse you. So, all right, that's where we are, right? Now, if I let u be the bottom, the derivative of that is up top, except that's not, right? That's no good. So I'm going to split this into two integrals. The first integral is going to be this over that, and the second integral is going to be this over that. This over that would be a basic u substitution. By design, I've designed it that way, right? Take the bottom, take its derivative, that's the top. You've got like 1 over u du, it's going to be beautiful. This one is a constant over an irreducible, and we will have to complete the square. There's no way around it, okay? But it's now doable, right? Let me do the actual splitting. I'm going to leave that up there because that's like, I wanted that up there. I want to keep it there. So here we go. I'm splitting into two integrals. The first integral is this one. And then I have, I'm going to write it this way, plus 1/8 integral. I had -4 over 4x squared minus 4x plus 3 dx.
So you're not going to pull the constant?
I am going to pull the constant out. I just want everyone to see the splitting, and that real important that 1/8 passes to both of these integrals, right? The 1/8 goes to both of them. And then I'm taking, those first two terms on top of that, and then I'm taking that third term on top of that. Again, I can't stress enough that the whole reason I'm doing this is because I wanted to design an integral that would be easy for me to solve. This one's easy for me to solve because the derivative of that bottom is exactly on top.